We're going to look at 3 exercises in section 4.1. The first one is exercise 13. Find any critical numbers of the function. G of t is equal to t times root 4 minus t for values of t less than 3. First of all, let's review what a critical number is. I sketched a graph here, and we're going to say that this is the function f, not g, and that our independent variable is x. So we're going to talk about the function f of x here, and later on we'll adapt to g of t, but f of x is just a general case. It's better to start with that. So a critical number is a value x such that either f prime of x equals 0, which means horizontal tangent, or f prime of x is undefined. But there's a caveat for critical numbers. F of x needs to exist. Okay, so let's have a look at the sketch above. F prime of x equals 0 means that this value down here, let's call it a would be a critical number because f prime of a is 0. This b would be a critical number because in this location f prime of b is undefined, there's a sharp turn, but we still fulfill the requirement that f of b exists. There is a point here. Now there's one more critical number, and it's right here for the same reasons as a. Here f prime of c equals 0. What is not a critical number is the value, let's say it's called d. Even though f prime of d is undefined as a vertical asymptote, there is no point here. F of d is also undefined, so we do not count this as a critical number. So let's look at what it means in our exercise 13. We need to find where g prime of t equals 0 or g prime of t is undefined for a point that is on the graph. So firstly, let's rewrite g of t as t times 4 minus t to the power of 1/2, because when we differentiate, it makes our life much easier. This is a product, and so we need to use the product rule, u and v. So u prime v plus u v prime, and the derivative of 4 minus t to the 1/2 is 1/2 4 minus t to the negative 1/2 times the inside derivative, which we tend to forget. 4 minus t, the derivative is negative 1. So let me clear things a little bit. This is 4 minus t to the 1/2 plus, actually minus, I'm going to take the negative 1 here and put a minus, and there's going to be a fraction here. T is on top, but what is at the denominator? We have 2 at the denominator, and we have 4 minus t to the power of 1/2. So this power of negative 1/2, now I put it at the denominator, and this is what it looks like. Maybe it's even easier to write square roots now. It's the square root of 4 minus t minus t over 2 square roots 4 minus t. And we're going to have to solve this g prime of t equals 0 or g prime of t undefined. So g prime of t equals 0. That means 0 equals square root of 4 minus t minus, might look like it's going to be difficult, but it's actually not so hard. If I add this term to both sides, I get t over 2 root 4 minus t equals root 4 minus t. and then if I multiply by the denominator, I get t equals 2 times square root of 4 minus t times square root of 4 minus t. So basically square root of 4 minus t squared, and so it's just 4 minus t. Think about this step, how it worked. From here, we are not going to find it very difficult. I'm going to distribute. This is 8 minus 2t. So adding 2t, I get 3t equals 8. T equals 8 over 3. This is the first critical number. I don't need to worry really about whether t equals 8 over 3 exists, because if the derivative exists, then it means there was a point there to start with. Secondly, I need to check places where the derivative would be undefined. Let's do it here, g prime of t undefined. And where could this happen? Well, if we look at g prime of t here, it's going to be undefined when t equals 4, because that's going to be square root of 0, which is fine, but it's going to be something divided by 0. However, so t equals 4 seems like a candidate. However, the issue is that it is not in the, right here, it is not within the domain that we are given. T has to be less than 3. So this one does not count, not in the domain. Okay, so when we look for critical numbers, we are not interested in endpoints. Endpoints are only something we look for when we have a closed interval anyways. We'll talk about that more in the near future. Now we're going to look at question 15. It's the same expectation. We are looking for critical numbers of a function. So this time it's h of x equals sine squared of x plus cosine x, and again the domain is limited to the open interval from 0 not included to 2 pi not included. So this is an open interval, it's not a closed interval. Closed interval would be if there was less than or equal, and if there were closed intervals, then that means something else if we look for absolute maxima and absolute minima. So let's go through the same steps as before. We need to find h prime of x, set it up equal to 0, and find where it's undefined as well. So derivative of sine squared x, this is a chain rule. We have the square outside, and the inside function is sine x. The derivative is therefore 2 sine x times the inside derivative, which is the derivative of sine cosine x, plus the derivative of cosine x, which is negative sine x, so we get minus sine x. Where is h prime of x equal to 0? Let's set it up. 0 equals 2 sine x cosine x minus sine x. We can factorize sine x, so it's sine x times 2 cosine x minus 1. And we can see how we can split this into two cases, either sine x equals 0 or 2 cosine x minus 1 equals 0. When is sine x equal to 0? There's infinitely many solutions, but not in the interval that we're given. The solutions in general are x equals, the easiest one is x equals 0, then x equals pi, then x equals 2 pi, and so on. And before 0, it would also be true that sine of negative pi equals 0, and so on. However, on my interval, x has to be between 0 not included and 2 pi not included. So there's only one, this one here, x equals pi. So that's my first critical number. The other way that h prime of x could be equal to 0 is if 2 cosine x minus 1 equals 0. So let's solve this one. 2 cosine x equals 1, cosine x equals 1/2. Using what you've learned in pre-calc, you should be able to find that, let's make a little sketch. Cosine of x equals 1/2, x is an angle, it's going to happen here and here. Now, for the one in quadrant 1, it's easy, x equals pi over 3. For this angle here, it's tempting to say negative pi over 3. Let's write this down. But negative pi over 3 is not going to be in my interval. So how can I talk about this angle? I need to go around like this, and that is 5 pi over 3. What you do is, from negative pi over 3, you add 2 pi. Negative pi over 3 plus 2 pi equals 5 pi over 3. And there would, of course, be more. We can take the angle pi over 3 and add 2 pi, and that would yield 7 pi over 3. And so on and so on. We can add 2 pi or we can subtract 2 pi, and it'll keep on giving us correct values of x where cosine x equals 1/2. However, again, which one of those are in the interval that we are expected to find values? There's pi over 3 and 5 pi over 3. Everything else is outside of the open interval. So x equals pi over 3 and 5 pi over 3. Are there any place where h prime of x is undefined? And the answer is no. Nowhere. Sine x is defined everywhere, cosine x is defined everywhere, there's no division by 0, there's no square root, tangent is not involved, so there's never going to be a place where h prime of x is undefined. So we've got our three answers: x equal pi over 3, pi, 5 pi over 3. Finally, we're going to look at one more exercise, which is question 27. In exercise 27, we're supposed to find we're supposed to locate the absolute extrema of the function on the closed interval. So here we have a closed interval. How does that impact our work? Typically, if a function was defined for all real numbers, the place where you would have relative max and relative min would be where we have critical numbers. Here is a max because f prime of x equals 0. Here is a min because f prime of x is undefined. Here's another max, here's another min, and that's it. But when you have a closed interval, suddenly you add another possibility. For example, if the closed interval is from 0, so we're starting at 0 to this number here, to a, if the closed interval is 0a, now suddenly a will yield an absolute maximum, or also a relative maximum, because it's higher than every other point in the interval given. So endpoints are important if we're looking for absolute or max or absolute min. And it's not a critical number, right? The derivative is not 0, and the derivative is not undefined here. So let's look at this function. We are going to want to find where y prime equals 0, y prime is undefined, and endpoints. I'm going to list them: candidates, y prime equals 0, y prime undefined, and endpoints. These are the critical numbers that we just talked about earlier. And there's the same rule that if y prime is undefined, the point needs to exist. If it doesn't exist, obviously it's not a max or a min. So let's find y prime. The derivative of 3x to the 2/3 is going to be 2/3 times 3x to the negative 1/3 minus the derivative of 2x, which is 2. That can be written 2 over cube root of x minus 2. Y prime equals 2 over cube root of x minus 2. All right, so let's start. Let's find where y prime equals 0. So 0 equals 2 over cube root of x minus 2. I'm going to add 2 multiply by cube root of x divide by 2 and find x equals 1. So that's my first candidate. Secondly, where is y prime undefined? Y prime is undefined when x equals 0, because we would have 2 divided by 0. And lastly, what are the endpoints of my interval? Is it a closed interval? Yes, because we have these brackets. So the endpoints are x equals negative 1 and x equal positive 1. So it looks like we have 4 candidates. In fact, there's something a little surprising here that's not usual. X equals 1 qualifies twice. If we want to make a sketch of this function, even though I know nothing of it, it appears that not only is 1 the endpoint, but it's also a horizontal tangent. Maybe the graph does like that. So it qualifies twice. We will only look at its value once, of course. So how do we find the absolute min and absolute max? We just list our candidates. We know one of them is the absolute min and one of them is the absolute max. We have negative 1, 0, 1, and we calculate the value of y. Not y prime, y. We're going back all the way to the beginning. When x equals negative 1, what is the value of y? So x equals negative 1, this can be written 3 times x squared cube root. So when x equals negative 1, it becomes the cube root of positive 1, which is 1. 3 minus 2 times negative 1, which is 3 plus 2, and so the answer is 5. Let me rewrite y here. It's going to be easier. There you go. What if x equals 0? 0 squared is 0, the cube root of 0 is 0, so we have 0 minus 0, y equals 0. What if x equals 1? 1 squared is 1, cube root of 1 is 1, 3 minus 2 equals 1. And now all we need is to observe what outputs we got. 5 is the greatest, so this is the absolute max. 0 is the lowest value, it's the absolute min. The function appears to do something like that. It starts up here at 5, goes down to 0 when x equals 0, and then back up to 1 at x equals 1. 1, 5, negative 1. And somehow there's also a horizontal tangent here, but we don't really care about that. So just to remind you, we will never in AP Calculus AB ask for absolute max and absolute min on open intervals, because it brings up some kind of difficulties if we have some if we have some asymptote in the middle. So the question absolute extrema is always going to be on a closed interval in AP. Doesn't mean we couldn't do it in another class or in college, but in AP, absolute extrema are always going to be tied with questions that have a closed interval. Now, if we don't have a closed interval, if it's an open interval or if it's just all real numbers, then the question will be find relative extrema, either minima or maxima. That's it for this lesson. Thank you.